Hi there, this is part 3 of repairing and upgrading this vintage DATRON 1038 True RMS meter. After repairing the meter in the first part, part 2 was about getting the power consumption down to avoid overheating. This was by installing a bigger rectifier at the rear panel where it did not heat other components, and replacing 17 of the 27 standard TTL chips with LS versions. That resulted in an almost 25% reduction in current draw on the 5V rail. But then I noticed a weird behavior on the threshold between 0.9999 and 1.000. Sometimes the last digit stays at 0 instead of going to 9. Something is definitely wrong. Let's have a quick look at the schematics. The two transistors down there form a generator producing 500 kHz adjustable with R37. This feeds M17, the first of 4 7490 BCD counters. A 7490 chip has 4 flip-flops inside. With pin 1 connected to pin 12, it counts in binary from 0 to 9. Note that QD, which represents 8 in binary, stays low for the first 8 counts and high for the next 2. This means QD produces exactly 1 rectangular pulse in every 10 counts. It can therefore be used as an input to the counter of the next decade. This is what you see here. Pin 11 is QD and feeds pin 14 of the next decade. With 500 kHz input on M17, M18 gets 50 kHz, M19 gets 5 kHz, and M20 finally 500 Hz. QD of M20 is only 50 Hz or 1 pulse every 20 milliseconds, and this is what is used to trim the frequency of the generator and thereby the integration period as showed in part 2. Of course, in a 60 Hz country, you would trim the generator to produce 600 kHz. The last QD signal drives 2 additional in-series flip-flops not shown on the right. The first to produce the leading digit, which can only be either 0 or 1, and the second the overflow. All in all, the counters can go from 0 to 19,999. I'm not going to elaborate how the AD conversion works, but very simplified, the capacitor is charged with a voltage to be measured and then discharged while the counter is counting. The higher the initial charge was, the longer the discharge takes and the more pulses are accumulated by the counter. When the charge in the integrating capacitor reaches 0, the count is latched for display and everything repeats. The latches are 7575 chips. Each chip has 4 latches shown as boxes here. As long as the control C is high, the output Q follows whatever happens on D. When C is low, the output freezes on the last value of D that got in. Although there are 4 latches in a chip, there are just 2 control pins on the outside. Each of these controls 2 latches simultaneously. The controls of the latches are driven by a monoflop circuit on the left connected to the controls of the latches via an inverter gates. Normally the monoflop output is high, which means the values in the latches are locked and do not follow the counter. When the integration capacitor has been discharged, the monoflop is triggered and its output reverts for about 10 microseconds to allow the latches to take the current counter values. So there are plenty of delicate timings that can go wrong. The latches may lock at slightly different times from each other and the counters can roll over while some latches are still open. Also, I'm confused why the controls for all latches are driven in parallel except for M11, which is split. Another possible source of trouble if the 2 controls are of slightly different durations. Just in case, I replaced M10, the latch chip, for the most right digit. That seemed to have an interesting effect that the problem has moved up 1 digit to M11. That's the one with the split control inputs. These are the 2 control inputs from the M11 latch. Each is driven by a different inverter gate, but from the same monoflop signal, so they should be identical, and they are. I just wonder why DATRON went through this complication. I had a look at the inverters that drive the 4 latches, and their outputs are here. M10 is controlled by the blue signal, M13 is controlled by the purple one, M12 by the yellow one, and M11 by both the yellow and the blue one. This all looks fine. It appears that the latches are not to blame. Just in case, I replaced all the 74LS75 with the original 7475 and it made no difference, so I swapped them back to the LS variant. This leaves the counters themselves, so I replaced the 74LS90s with the original 7490s. and the problem has gone away. I have to admit that I don't quite understand what caused it in the first place and why it went away using the original counters. It looks like a glitch caused by the mixing of logic families that are supposed to be compatible, and are, mostly, on with the calibration. As a prerequisite, one has to adjust the analog to digital converter on the top PCB. Disconnected from the analog board, I have to feed it directly with exactly 1 volts DC and adjust the readout to match by adjusting the reference voltage. That readout was fine with 4 digits, but with 5 I can't get it below 1.0004 volts. Here's the relevant part of the schematic which produces the reference voltage for the ADC. The adjustment is done with R86, which is in series with R85, and the whole thing has R87 in parallel. The manual states that if the range of R86 is not sufficient, the factory selected resistor R87 needs to be replaced with a new selected value. But how to select a new value? I desoldered one leg of R87, which, like all factory selected components, is conveniently mounted on posts, and then connected the 2 posts to a resistor decade. Starting from 220K, I dialed in some values and tested the range of R86 until a standard 200K for R87 seems to be a good choice to cover what's needed. With that value, I can change the meter to read from 0.996 volts all the way to 1.01 volts, and of course to the desired 1.0000 volts. I replaced my decade with a 200K metal film resistor from Vishay selected for low temperature drift. The new R87 is partially obscured by my probe feeding the 1 volt DC needed for adjustment. And with that I can finally adjust the ADC to the desired 1 volt readout. There are a few additional steps adjusting the inner workings of the RMS converter, but essentially it comes down to these here. 5 different ranges need to be calibrated, by first using a 420 Hz signal of a specified voltage and adjusting trim pots in the attenuator to give the correct readout, and then a second pass using a 25 kHz signal of the same voltages but adjusting a trim capacitor instead. The adjusting is far easier said than done because the shield prevents you from seeing where the trim pots and trim caps are and slotting the non-metallic adjustment tool in for turning. The holes in the shield are by no means exactly centered on the pot or cap. All that means a lot of time-consuming probing before any adjustment can be done. To make it a little easier, I labeled the holes in the shield with a pen, but there were still 2 instances where I mixed them up, resulting in accidentally messing up an already calibrated range. Because of the time each adjustment takes, mostly in fishing for the slot to insert the tool, the instructions in yellow prove to be really time-consuming. After every adjustment, I basically have to close the lid for 15 minutes to allow the temperature inside to go back to nominal before trying the next adjustment. Here is, for example, the 1 volt calibration. The playback is significantly accelerated. Taking the lid off is not that easy to start with, and fishing for R40 proved to be tricky, even with a torchlight to align my adjustment tool. From beginning to actually adjusting took 2 minutes and 20 seconds. I think I'd rather spare you to see every one of these adjustments. Instead, I thought to finish off with going over some of the buttons the DATRON 1030A offers. The only button that doesn't do anything is the remote proc, because that option is not in my meter. Normally the meter is AC coupled through an internal capacitor, so the meter only shows AC. When pressing the DC coupled button, this capacitor is bridged and the meter now shows you the AC plus DC voltage of the input, but of course nothing stops you from just applying DC and using the DATRON 1030A as a DC voltmeter. The next button is band limit. Normally the DATRON 1030A measures to 1 MHz, but if you don't need that range, you can reduce noise by this button, which enables a low pass to reject higher frequencies. It is -3 dB at 10 kHz. I'm feeding a 1 volt signal of 10 kHz, and if I lower the output of the generator by 3 dB, the voltage drops to around 0.708 volts. I should get the same result if I raise the voltage again, but put the band filter on. And here you have it. And of course, removing the filter restores the full voltage. The LF button is for measuring frequencies less than 40 Hz. If I change the generator from 10 kHz to 10 Hz, the meter is not happy. Pressing the LF button lowers the minimum frequency to 1 Hz, but at the price of having to wait much longer for the display to settle down. The spec says a settling time of 15 seconds in LF mode. Last is the mean square button. I don't really know why one would use it, but anyway. Basically, instead of RMS, the display shows the mean square value, so RMS without the R or root taken. Input in this test is a voltage of 0.5 volt RMS in the 1 volt range, and if I press the mean square, I get 0.25 with a cute voltage to the power of 2 Fs symbol. The square of 0.5 is indeed 0.25. Here's another example, 0.3162 volts in the 1 volt range, and the square should be very close to 0.1. And it is. Things start to get confusing when you leave the 1 volt range. Here is 2 volts in the 10 volt range. The square of 2 is 4, so I would expect to see 4 as mean square, but instead I get about 0.4. And a similar thing on the other side of the 1 volt range. 31.62 millivolts squared should be close to 1 millivolt, but instead I get close to 10. Notice that the unit has now an extra m. It has changed to millivolt square over Fr. It took me a while and a few tests which you see in this table to work this out, because the manual is not very helpful in that aspect. This section here is all you get. The penny dropped when I finally realized that Fr stands for full range. Everything is fine in the 1 volt range with Fr equal to 1. If you measure in the 10 volt range, the mean square value is shown as voltage square over Fr or voltage square over 10. So to get the correct value, you have to multiply by 10. This turns 0.403, as in this example, to 4.03 volts square. In the 100 volt range, the value is shown as voltage square over 100. So you have to multiply by 100 to get the correct number, and that works out just fine, as you can see in these examples. Going the other direction, 100 millivolt range, now the mean square unit symbol changes from volt square over Fr to millivolt square over Fr. Because of the millivolts, the correction factor is 0.1 in this case, and multiply that with a readout. This turns the display 10 into 1 millivolt square, which is the correct value. Again, the same applies for the 10 millivolt range, except now we're using 0.01 as a correction. If you think about it, scaling the result by volts or millivolts over Fr is a pretty neat trick to ensure that the square of the measured voltage fits on the display without needing a range change, because the 1030A is of course not auto-ranging. But that got me thinking. In the 1 volt range, for example, the DATRON display can show up to 1.9999, so the trick only works if the input is less than the square root of this, that is 1.414. This here is a value that is close to the max, certainly more than 1.414, and sure enough, mean square produces an overflow. I have integrated the DATRON 1030A into my bench equipment sitting above the Racal 9300, which does kind of the same thing but hasn't got a digital readout. To be fair, both meters have a DC output at the rear, allowing the hookup of an external digital multimeter to read in parallel with the built-in one. I have used that often for the Racal. The Racal has the edge in that it can go much higher in frequency and is more sensitive, down to 0.1 millivolt full range. But the DATRON beats the Racal in doing AC plus DC or just DC, and definitely its digital readout is more convenient to use. So for now at least I keep both. If you like my videos, don't forget to subscribe, and it would be great if you decided to become a Patreon. That would really help this channel. The link's in the description. As Patreon, you always get early access to videos, a blog and other exclusive content. Thanks for watching.